This conference will now be recorded.
Good morning, everyone. Thank you for joining today for this session where we try to understand what is formal verification. I am Ravi Marathe. In the past, I have worked on different chip design companies on various aspects of design and verification. I have worked both on simulation verification, that is dynamic verification, as well as formal verification. Now, let's see. Over the next 4 weeks or so, let's try to understand what formal verification is, what are the different concepts, the different terminologies, how to apply them to the verification activities in your hand, and we will get this understanding both theoretically and practically. We will see some examples of how to set up, how to write properties, how to run the properties, and get some conclusions at the end. On completion of this course, I'm sure you would come out confident on using this new technology in your daily verification life. You would be able to confidently involve yourself into discussions in the teams where formal verification is being discussed. During this course, we will also understand where you can and cannot apply formal verification, and some of the techniques for getting successful results. And we will also look at some basic concepts and constructs of system Verilog assertions. We'll see how to write properties, how to use the coverage flow in the sign-off process. Now, what is verification? In general, we hear this term verification many times in our life. There is identity verification, address verification, and so on. It's basically they are trying to make sure you are the person that you have declared, or the information that you have declared about yourself is true. Now, in the context of VLSI, it is making sure whatever is coded in the RTL is in compliance with the protocols or the specifications or the architecture documents. Or in other words, if you have to ask a question, have all the features listed in the spec have been coded in the design, or does the design behave as described in the function spec? Are the features implemented in the same way as in the architecture spec, and so on? If you have all these questions, the answer to that and the process of answering all this is the verification process. Now, at a high level, there are two types of verification we can classify: dynamic verification and formal verification. We will look at both of these in little detail in the next few slides. But before getting there, let's understand the VLSI design life cycle. So in the beginning, you get the requirements or some specification from the customer or the marketing team. Then the architecture team comes up with a high-level architecture plan as to what kind of components to be used, which processor to be used, what kind of IPs to be used, and so on. Post that, there is RTL coding phase where each of the features is implemented in Verilog or VHDL. and then the generated code is synthesized and a netlist is generated where all the behavior that is coded in the RTL is now in terms of gates and flops. Then it goes through the place and route phase, then it goes into fabrication, and finally after testing the chip, it goes into production. Now on the verification side, parallel to the specification and architecture phase, in the verification side, there is verification planning going on. So as to what kind of technology is to be used for verification, whether it is simulation or formal, and what kind of test bench architecture it has to be created. Do you reuse from an existing one? Do you write the whole thing again? What kind of scenarios do you need to do emulation and so on? Once the planning phase is done, then you get into the RTL level verification phase. This is where the coded RTL is being verified. This goes in parallel with the RTL coding phase. After that, there is a netlist level verification, which goes parallel to the synthesis and place and route. And finally, there is post-silicon validation, which comes after the fabrication phase, where the chip is ready for testing. See, here you see there are 4 phases in the verification. One is the planning phase, the RTL verification phase, netlist verification phase, and the post-silicon validation phase. In all these 4 phases, in some way or the other, the formal technology can fit. It can be used in uh, verifying certain aspects of the each phases, either the specification, RTL, or the netlist, or the silicon itself. Now going back, let's also just see what are the phases in dynamic verification. You have the verification planning. As we discussed earlier, you decide what all components are required, how the test bench is architectured. This phase is common for both simulation and formal. This is the place where you decide which blocks go into regular simulation, which use formal. Do you use formal and simulation together, or do you use only formal, or do you use only simulation, and so on. Then you get into the test bench environment phase, the test bench coding, test case coding, regression, coverage closure, and sign off. In the test bench coding phase, you see that there are multiple components being created: the stimulus generator, driver, monitor, checker, scoreboard, sequences, and so on. These are the main blocks required for the test bench to function properly. And the test case, which is written on top of the test bench, does the fine tuning or configuration of the stimulus, and also you can write additional checkers into the test case and so on. In the dynamic verification, the input to the DUT is modified on every cycle, or the value that is provided to the DUT changes at different time intervals, and so does the output from the DUT change at different time intervals. That's why this is called a dynamic verification, because everything is changing, whether it may be the inputs, the outputs, or the internal signals. Everything is being changed. You can see that using a waveform in the simulator. And the simulator by default doesn't drive anything. So if you don't drive anything as part of the test bench, you will see X's, the unknowns, being driven to the DUT. In the waveform, if you open up, you will see all signals having X value, unless it is driven from the test bench. Now, as a combination of test bench and the test cases, you configure and constrain the different inputs of the DUT, and through the driver, you drive them onto the DUT. So you understand this, that the initial input space of the simulation is 0, and you build on that as in configuring the different inputs at different times. So you update or modify the input space as in when you progress in the simulation. That's why this is termed as a 0 plus process. Now this is how you can visualize a dynamic verification. Here the stimulus that is generated through the test cases gets driven onto the DUT through the driver, and it reaches the checker, the output reaches the checker, and there is a comparison happening with respect to the expected value. Now if you look at an example of an OR gate, so we know this truth table of an OR gate, that the output is 0 when both the inputs are 0, and in all cases the output is 1. Now if you have to simulate this, if you have to verify this in simulation, you have to provide different values at different times. So initially you drive zeros to both A and B, and then check the value of Q, that it is 0. And later, to verify other set of values, you explicitly drive those values, 0 1 1 0 or 1 1, this combination, and each time you compare the value of the output to see the correctness of the logic behavior. Similarly, you can see a mux. This is the case where select controls what gets driven on the output. So to verify this again, now you have 3 inputs, A and B and the select. So all 3 you need to drive to compare the output value. Here you can see all the different values are being driven, and the corresponding output is being checked. So if you do not specify any input combination, that particular input set will be ignored, as in it will not be verified as part of the test case. So that becomes a hole in your verification. So everything will have to be explicitly coded. All the values will have to be explicitly coded in the test case. I mean, there are other scenarios of doing random verification where you don't have to explicitly write the values, but you can randomize the values. But the control still is with the test case or the test bench environment, where you have to specify that you need to randomize a particular value. Now, in case of formal verification, the life cycle looks very similar. You have the verification planning, the test environment setup, the test bench coding, regression, coverage closure, and sign off. The thing that you see missing here is the test case generation. Now, test case is not necessary here because you are not providing any specific stimulus. In the test bench coding phase, also you will see very few components. You need to write assertions, covers, and assumes, and optionally in some cases you can have scoreboards. There is no necessity of writing stimulus generator, monitor, etc. So a big chunk of manual effort of what values to generate, when to generate, how to drive, when to drive, all those questions need not be thought of by the user. User just needs to think of what to check rather than how to check. How to check is taken care by the tool itself. Now in the running phase, you see again the similar steps, running assertions, debugging the failure, analyzing the coverage. There are two new things that you will see here as analyzing complexity and applying simplification. We will understand these two better as we go forward in the course. Formal verification, what is the difference between formal verification and simulation? In dynamic, we saw each values are driven at different times and the output is compared. In formal, the verification process is done in the mathematical world. So mathematical modeling methods like satisfiability, binary decision diagrams, inductions, model checking or bounded model checking, and so on, are employed by the tool for doing this checking. At a high level, there are two types of formal verification. One is equivalence checking, another is property checking. And in equivalence checking, there are two versions of the design which you are comparing. It could be two RTLs that you're comparing, two designs written by two different users, or there is some optimization done in one version and you want to compare with the original version, or a post synthesis, you want to compare the netlist to the RTL and see if there is no issue with the synthesis process. Or the other option or other type of formal verification is property checking, where you describe the behavior of the design using assertions, and the design behavior the RTL design behavior is compared to the behavior that you have written in as part of assertion. Now the techniques that we see here, those satisfiability or BDD or inductions, you need not get into the details of that. You need not understand what it is exactly, because they are encapsulated as form of algorithms, and they have created something called as engines. Each engine employs one or more of these techniques, and the tools allow us to choose different engines at different point of time, or they also have this orchestration where they can automatically pick these different engines based on the design or based on the properties. So for curiosity or for understanding what it is, you can study these, but it is not required. And we are not going to look at this as part of this course. Now we saw that dynamic simulation is a 0+ process, where initially there is nothing driven by default, and the input space will have to be built or modified by the test bench. On the contrary, in formal verification, it is infinity minus, that is all possible values. When I say infinity, it is not the infinity that we have learned in mathematics, that is unlimited. Here by infinity, what we mean is all possible values in that context. Suppose a module has 5 inputs, and all possible values of inputs for this particular block is 2 to the power of 5, which is 32 different types of inputs. So we are talking about 32 here, which is all possible values. And then using constraints, we can control or reduce what values are required and what values are not required, and also the sequencing. So on every clock cycle, 32 different values are tested. Now you may want to control on the first cycle certain values are required, and second cycle different set of values are required. So that is controlled using the constraints, what is called as assumes in SVA. The visualization of this formal verification process is like this. You have the duty, and around that you have the constraints and the assertions. The constraints, as we saw, control the input space of the design, what values the tool uses in verifying, and the assertions are the checking mechanism. They check the behavior of the design. Now going back to the same example of OR gate, we simply write this property, assume property at positive of the clock, Q equals to R of A and B. Now this is the way we describe the behavior, and this is used for checking the design behavior by the tool. Now here we don't provide values to the tool. As we saw in simulation, we don't say drive 0 or drive 1 and drive 1 0 1 1 and so on. The tool converts the design and the behavior flat into a big Boolean expression or a big state machine, if you want to call it. Once it has a Boolean expression or a state machine, then it runs the engines on this. So basically, all the processing happens in the mathematical world, and then it tries to evaluate the correctness of this behavior. Similarly, for the mux case, we write two assertions, one each for select 0 and select 1. Now let's look at how to do this in the tool. Let's see a quick demo of using this in the tool. Let me share the screen. Now let's look at, I have already coded the target. Here you see the OR gate. So I have two inputs, in 1 and in 2, and out is assigned the OR of in 1 and in 2. The test bench for this OR gate is in 1 in 2 and out 1 in the test bench, and we have instantiated the OR gate, and then we have this assertion where on the positive edge of the clock we are comparing the outputs to be the OR of two inputs. The syntax is you write a label, then the keywords assert property. We'll understand this later when we look at how to write system log assertions. Here you write the clock event. This describes when to perform this check, and we are saying this happens on the positive of the clock. And then you write the behavior, close the bracket and semicolon. Keep this commented. And in the tickle file, so the tickle is the language used by most of the tools, TCL. There are many keywords like read file, create clock, sim run, sim save reset, check FE, and report FE used in this test. Read file is used to compile the design files, and these are the different options passed to the command. Create clock is the one which creates the clock of period 100. Now this is not required for the design, but it is required for the assertion. All assertions are sampled on a particular event. Now this is a step required by the tool, so they run some initial analysis. They run some initial simulation to get the values stable. We save that and then we run the formal check. Now let's run the tool in GUI mode. VCF-GUI is the command. VCF is a tool provided by Synopsys, and Cadence provides a tool called Jasper. So you could use either of the tools, whichever are available with you. There is another tool, OneSpin, or it's also called the QuestaSim by Mentor. So if you have access to that, you could use that as well. Now let's source the rtest.tcl. It runs the commands that we have provided in the TCL file. So let's go up and see what it has done. So this is the place where it does the read file. It compiles the design, it synthesizes, and also takes in the assertion written in the test bench, which is shown here. And then when we do check FE, it picks up the license and then starts running. And finally, the report FE shows the result. It says one assertion was found and that was proven. So here you see how long it was run, what was the type. So we'll understand in detail during the course of as to what this GUI is. We'll understand this GUI. Now, similar to this, let's also take the mux. You have the mux here coded, and there is a mux test bench. Mux test bench. We declare the in1, in2 cell and out in the test bench and the clock, instantiate the mux, and we have written the properties. In here you see there are two assertions written. When a select is 1, the out 1 should contain, or out 1 value should be equal to the in1 value. And when cell is 0, out 1 value should be equal to the in2 value. Now let's run that. Let's restart this VCF so that we can run a different design and different set of assertions. Let's run the mux.tcl. Here we had written two assertions, and we'll see two assertions being loaded here, and it runs and it says that they are proven. Now I also have written a test for flop, where we similarly write a flop, we create a test bench for the flop, and then we have this assertion. But I'm not going to run this, but I will run another test bench where I have all the three blocks instantiated together. So you have the flop, you have the flop, you have the OR gate, you have the mux. So let's run that. Let's restart the VCF first. Here I'm just quickly showing you how to run it in the tool. The different, I'm not going in detail here. We will go through this as we go deeper into the course. TCL. So we have the flop assertion or assertion and the mux assertion written all together here. Now you see it runs one by one and it shows that all four have passed. Okay, now let's go back to the slides. Okay, we'll continue from where we had left. So we saw how we can write properties and how to run it in the tool. Now let's see what all the different things that we do as part of formal verification, to where it can be applied. Earlier, while we were discussing on the life cycle of verification, I mentioned that it can be used in planning phase where architecture is being built. So some tools provide ways to model the architecture without writing a single line of code. So formal verification can be used as soon as idea has come up in the mind, and you want to make sure that in that particular architecture there is no deadlocks or things can move smoothly. Then it can also be used by the designers, as and when they are writing the code, they can simply use this tool to make sure the piece of code that they have written is functioning fine. There are no uh, easy issues or uh, trivial issues in the design. They can use it to explore the design, as in what all it can do. If you're writing a state machine from one state, where does it go, where all it can go, and so on. And then finally, it can also be used by the designers to run a few set of assertions always before giving it to the verification team for them to do a thorough verification. Now, the third usage is by the verification engineers itself, which is their main job to do verification. And formal verification by nature does checks all possible values we saw earlier. So it can be used for exhaustive verification. And by using constraints, you can also control what to verify. And so it can be used as bug hunting as well. One is the bug absence method. Another is the bug finding method. Then finally, it can also be used as sign off. Now, what are the different types of designs it can use? Primarily, it is the control path verification. Data path verification also can be verified. But in this slide, we are looking at the different control path designs that we see commonly in the industry. That is different decoders, arbiters, bus bridges, DMA controllers, power management units, bus interface units, schedulers, interrupt controllers, memory controllers, token generators, cache coherency, credit manager, standard bus interfaces, proprietary interfaces, clock and reset control units, and IO muxes. When you see these kind of blocks in the design that you are trying to verify, you can give the formal verification a chance to verify some of the features from there, either some of the features or some of the units or some of the blocks. So when you're deciding to choose, you can apply this either at a feature level. So you might say this particular feature in this design I will verify using formal verification, or a subunit, a small area, a few files, or the entire unit you can sign off using formal verification, or you can go further higher to subsystem level or cluster level or system or SOC level. And this is not just at RTL level, you can use it at netlist also. So some amount of verification can be done at netlist level also, though it is not necessary because all functional verification you would have already done in RTL phase. And the synthesis, post synthesis, you can simply do equivalence checking, and that should do it. You need not get into the functional verification of netlist again. But for timing closure, once you have the timing, then that may cause some issues. So you have the timing simulations in the dynamic verification method. Here, a formal can also be used as an aid for doing timing closure or place en route to finding what is the maximum delay, what is the maximum number of clocks it takes in a particular path, or where on which particular node, on which node there is a lot of activity. So you can avoid placing high activity nodes close to each other so as to reduce uh, high activity at the same point and increasing the temperature in that area. And also in post silicon debug, so when you see an issue on silicon, you can use a formal tool to try to give a root cause in RTL. So you take the symptom from the silicon, use that as a behavior, and write some assertion or property from that behavior and give that to the tool and ask it to show what kind of input scenarios can cause that behavior. So some tools allow uh, this particular method as well. Now, its verification can be done at different levels. One either at a local checker that is very specific to very close to the design, or at the interface checkers. So you want to verify the protocol compliance of an interface, or end-to-end checkers. So at a block when there is a lot of manipulation happening either on the control or the data, you want to verify from input to the output the control or the data is intact. So you can write end-to-end checkers, data integrity checkers. Security is a big concern nowadays. Security verification also can be done using formal verification. Basically, the main goal is to find that there is no unintentional corruption of any data or leakage of data. Connectivity can be checked. System level address maps, X propagation can be checked. Configuration register integrity, power checking. Low power verification is another big chunk of verification that happens nowadays. So formal can, by virtue of its exhaustiveness, can help us to do a lot of verification. Now, as we discussed earlier, there is absence of bug or presence of bug. So in absence of bug, we are saying this particular behavior has no buggy behavior in this design. Or if you want to check the presence of the bug, if the design is too huge and we are not able to get um, convergence of those properties, we can go for bug hunting mode, where on different paths we try to see if there is a bug. Then we go for, then there is checking reachability. If you have a particular behavior and you want to see if this is possible in this design, you can go for reachability checking. And there is coverage analysis here as well. There is slight difference between the simulation coverage and the formal coverage that we see. In simulation, the coverage that we see is a stimulus coverage. Since we are writing all the stimulus and the sequence of different values, we want to check the correct the how well we have written the stimulus, how well we have provided the stimulus to the DUT. So that's what the coverage shows in simulation. The simulation coverage does not talk about checkers. So even with 0 checkers, you can have 100% coverage possible. The coverage in formal verification is actually the uh, checker coverage. So how much checking you have done. Now stimulus, you don't have control, so but you can also measure it. As the complexity of the design increases, the tool may not have tested all possible scenarios in the time that you have provided to the tool, or in using the machines, using the power of the machine that you have provided to the tool. So we can check that as well. That is called stimulus coverage. And finally, confirming the bug. Uh, there might be a bug present in the design. Now the bug might be fixed in the design. If you rerun the test case in simulation, that might pass. But now, since the formal picks all values to test that particular behavior, now if there is a buggy scenario on a different path, on different set of values, it can show that as well. So basically, a particular behavior, you can make sure that it is fixed for all input values. That's all I have for today. See you next week when we go in detail and look at the system verilog assertions and other details about formal verification. Thank you.